Hi, welcome to our differential equations. Today's topic is going to be about linear equations. The method that we are going to learn today is called integrating factor method. This can be used to solve this category of linear first order equations. Integrating factor method itself is in fact the reverse of product rule of differentiation. I'm going to explain that. Also today we are going to learn about a couple of side topics. One is transients. Those are components of the solution that go to zero as you go to infinity. And also we are going to take a second look at so-called interval of solution. So first of all, what is meant by a linear equation? We had seen this thing once before. We are talking about the first order linear equation. So linear equation in y, we are trying to find y and y prime show up in our equation. They are multiplied by some known function, call them a of x and b of x, and when added up, it produces some, say, c of x. So a, b, c are some given functions or numbers, and our attempt is to find y. We spend quite a bit of time explaining that these type of equations show up in a very large variety of application problems. We mentioned them in the section on modeling, and later on we're going to come back to those topics. As a matter of standardizing our approach and our discussion, we are going to have something called standardized equation. We take this, multiply by the leading coefficient, and make it to look like this one. So the leading coefficient now is 1. So it's kind of standardization of our approach. To understand these topics, I've listed quite a few problems here. Perhaps we go and look at some of them and see how all these topics come about. Let's start with the easy one. Very first one, it says y prime plus y is equal to exponential of 4x. So we are looking for a function y that if you add to its derivative boils down to just exponential of 4x. First, we want to know how do we actually solve this, and then go ahead and talk about some properties of the solution. Is there any component that decays? On what interval is the solution valid? And other type of side topics. And then as we go down, the problems become a bit more complicated, and the algebra or the calculus of it increases, but the same approach applies to all of them. And the main thing is that we are actually applying the product rule. Let's just remind you what the product rule was. If I have u times v, two functions of, say, x, and I want to differentiate it, product rule said differentiate each of them once and multiply by the rest of them, and each term takes a turn to go through this process. So derivative of u times v and the derivative of v times u, that was what was product rule in calculus 1. That is what we are going to be basing all of our solutions on. Let's see how does this work with the very first one. Y prime plus y is equal to exponential of 4x. So that is example 1. How is this relating to product rule? You see that I have y prime, just like I had u prime here, and I have a y, and in that case that would be a u. So a function and its derivative show up. Well, the question is, what would be the missing component? What would be v and a v prime in that case that will make this problem match against that? That is the challenge that we are facing right now. Okay, so the question now we are facing is what's going to play the role of v and v prime? Well, we don't know, and here all I see here is just a 1, and of course derivative of 1 would have been 0, it wouldn't work. So what I think about is to take this thing and multiply by some as yet unknown function in the hope that the left hand side of this would be a match for what I have over there. So I'm going to multiply this thing by a m, multiply by some as yet unknown function. We call it m of x. Most textbooks use the Greek notation mu of x, but I don't see any reason to inject one more complication of some Greek letter in the middle of this. But in case you feel comfortable and when you're reading your textbook, you might see mu thrown in this case. But at any rate, I take this thing and multiply it by m. And to keep it look like that, I write it on the right hand side. So I'll have y prime times m. And then I have y times m. And right hand side is just e to the 4x times m. So multiply both sides of this equation by some as yet unknown function, we call it m. What is the purpose of this? Let me write the product rule right above this thing, and then you cross-check the terms of u prime v and then u v prime. So this m playing the role of that v, and m again has to be also v prime. Okay, so we are looking for a peculiar function which has the property that this is the derivative of that. So I want m to play v prime. I want m to also play v. So it means m prime is m. So the function that I'm after has to be such that its derivative is equal to itself. Well, we can go ahead and solve that side question by separation method, or we can just go ahead and guess right now in order not to take too long to what's a function whose derivative is equal to itself. Any of these functions would do, and of course non-zero. M is equal to exponential of x. Exponential of x is a function that its derivative is equal to itself. So let's go back to see what's the magic of this exponential of x. What does it do for us? Let's go back again and multiply this thing by exponential of x. So it becomes y prime exponential of x plus y times exponential of x, right hand side exponential of 4x times exponential of x. Right hand side looks a bit silly to write it like that. We write exponential of 5x. What have we achieved? What we have achieved is that left hand side is a complete derivative. That is, it's an example of this product rule. Let's see, what expression is it that if I differentiate will give me that? Well, definitely has to have a y in it, and it needs to have an exponential of x in it. By product rule, what would that be? Derivative of the first times second, that is that, plus first times the derivative of second. Well, the derivative of exponential of x happens to be exponential of x. That is a match for this. So that is equal to exponential of 5x. We have made a monumental advance in our problem in that we have converted it to something for calculus 1. I am looking at the function for a while. Don't look at the details of the interior of this. We have something whose derivative is exponential of 5x. So what is that thing? So it's a y exponential of 5x, exponential of x. Clean that up. y exponential of x is equal to the integral of exponential of 5x dx. Its derivative is this, so antiderivative is obtained by taking this integral. Well, that is exponential of 5x over 5 plus some constant. Now I want to find y, so I just go ahead and divide by exponential of x. So I will have y divide by exponential of x. So this is e to the 5x over 5 plus c over exponential of x. I can do this term by term. 5x divided by x, that's going to be exponential of 4x over 5. And this is c over exponential of x. You might as well write it as c times exponential of minus x. Okay, that is our solution. So this is the general solution of this equation. Depending on what c value do you take, you are going to get the whole family of solutions, and they comprise all the solution you could find. Okay, some side remarks with respect to this. What are the components of this? We see this exponential of 4x. You remember how exponential looks like, is that right? Exponential of minus x, that's the second component. Exponential of minus x acts like this. Because of applications in physics and engineering, signals or information that looks like this is called transient, meaning it goes away. So components of the solution that are transients, you just identify them. So this is going to be called transient. Now, is there any restriction with respect to what x value you are going to have? Well, no, there is nothing saying anything about any restriction about any x, and so that the domain of the solution is going to be from minus infinity to plus infinity. We are going to have more to say about this issue of the domain in perhaps a bit more interesting problem, but here is rather flavorless. The solution exists for the entire real number line. So let's go back and see what happened. Integrating factor. This m is called integrating factor. Integrating factor. Why is that called integrating factor? Because after I find this and multiply both sides with that, my problem can be integrated. You see what happened here? That's the magic of it. When you multiply by m, it makes the y component of the problem to be collected into a product that has been differentiated. So to go back to this, you're integrating, of course. So this is a factor that makes the integration possible. So that's why the method is called the integrating factor method. Okay, let's go take a look at something perhaps with a bit more turn and twist to it. Problem 2, 3y prime plus 12y is equal to 4. So problem 2 is 3y prime plus 12y is equal to 4. Okay, standardization. Divide by the leading coefficient, so it becomes y prime plus 12 over 3y is equal to 4 over 3. So y prime plus, well, that's 4y is equal to 4/3. Okay, so we are insisting to make the leading coefficient 1 so that different people can compare their notes. So if you take this equation multiplied by 2, it's going to be 6 and 24 and 8, and somebody else might divide it by some number. So how do we compare all of these? One way to do that is to make the leading coefficient to be 1. That's a very standard thing to do in mathematics. Okay, let's practice this thing again. I want to multiply it by something. so that the left hand side becomes a complete derivative. That thing that's going to perform this magic is going to be called integrating factor. So I want to have y prime times something plus 4, let me put the m next to this thing and a y, and right hand side is 4/3 of, well, there's going to be an m here. So in the product rule, you have something and its derivative, and these two have to play the role that the derivative of this one has to be that one. Don't get it wrong. M prime has to be 4m. Is that right? Let me remind you again. So I say u prime v plus, let me write it like this, v prime u. Okay, we wrote the product rule like this, u v prime. So I have the u prime and u. This item, when it is differentiated, has to produce that item. Okay, this item, when it is differentiated, has to produce that item. Well, you get again a separable equation. Let's write it separable. dm dx is equal to 4m, or dm over m is equal to 4 dx. Integrate both sides. We don't need to worry about the constants or the details of your logarithm. So to be quick, logarithm of m is equal to 4x. I didn't even bother with the constant. So m, exponentiate both sides, becomes exponential of 4x. So again, we did this thing very quickly. I didn't put absolute value, I didn't put a constant. I just need one m, any of the variety of them would do. So my m is exponential of 4x. What do? I take this y prime exponential of 4x plus 4 exponential of 4x is equal to 4/3 of exponential of 4x. What did this integrating factor do for us? What did it do? Actually, I forgot to put the y here. What it did is that left-hand side is the complete derivative. That is, if you wrote y exponential of 4x, so there is no guessing involved here. This is y, and this is just that. There is no work to be done. If you differentiate this, you get that, because derivative of the first times second, derivative of the second is just as you see it here, and right hand side is 4/3 of exponential of 4x. What do we do next? Well, we have the derivative, we integrate. So now calculus 1 kicks in, y exponential of 4x. The derivative of it is given, so what you want to do is take antiderivative. Hopefully that's a simple step that you can take the antiderivative. Sometimes it's not so simple, but that's beside the method we are presenting. Integral of exponential of 4x is exponential of 4x divided by 4. Is that right? Exponential divided by 4, so the 4's cancel. And now I do need this constant. So over there putting a constant was optional. It just clutters. But here we actually do need it. Now I divide by exponential of 4x. We always want to isolate y. When I divide, I just get 1/3 here because I got rid of this exponential. And when I divide the c by that, I write exponential of minus 4x. Okay, that is our solution. And what? Well, what's the transient portion of this? Transient portion of this is whatever constant you had, exponential of minus 4x. Interval of solution, well, there is no limitation anywhere with respect to what x should be. So we come here, look at our standardized equation. So, well, is there any limitation on x? Uh, no, there is no limitation, and so how about our solution? No limitation on our solution, and so that was easy. Let's move up one notch. So example 3, so y prime plus 3x squared y is equal to x squared. Okay, we want to put everything in a a quick black box and then get things done and move on quickly. And the procedure that we introduced before was, well, multiply by m, make an equation for m, solve that equation. All of that can be placed into a little machine that will do this for us. So if I have y prime plus, this is, we called it p of x after standardization. It's p of x times y. Right hand side, we called it q of x. M, that equation we had, is always a separable equation, and you can always solve it, and the answer is always exponential of integral of p of x, just like what we had here. M, if you look at here, this is my p. Integral of p is integral of 4. Integral of 4 is 4x. M is exponential of this. I got 4x here. M is always exponential of integral of the quantity that you had here. So you go ahead and double check that for yourself. You see that's the case. So with that shortcut, I can get my m a little bit faster. Exponential of integral of 3x squared dx. So once again, what happened? We make sure we are starting with a 1. It's standardized. Okay, let's make sure we don't make a mistake. If there is something other than a 1, we divide the whole equation by it so that we have a standardized equation. Then we pick up the coefficient of y. Then we integrate it. Then we exponentiate it. And then that's our magical integrating factor. Well, here our life is easy. This integral is x cubed. Let's see, does it stand to inspection? Let's go multiply this thing by exponential of x cubed. So I have the following. I multiplied both sides with the exponential of x cubed. Now, just to see what the magic was and just to make sure that we haven't made a mistake, let's look at this and what is here. This second red box has to be the derivative of the first red box. That is what m is going to do for us. This one is the derivative of that one. Well, what is so great about that being so is that the left hand side is a complete derivative. That is, if I had y times this expression, again, no guessing involved here, this y times that. If you differentiate it, by product rule is a y prime times the second expression. Derivative of second expression is that. Derivative of exponent times the function. Right hand side, I have x squared exponential of x cubed. So what is y exponential of x cubed? That's going to be anti-derivative of what I have on the right hand side. Okay, let's do a little bit of a u substitution. If I take u to be x cubed, du is going to be 3x squared dx. So that's going to be exponential is eu. x squared dx is du third antiderivative exponential of u third plus a constant. We do a back substitution, exponential of x cubed over 3 plus a constant. Now we divide both sides by this coefficient, so I'll have y is equal to that cancels, I get 1/3 plus c exponential of minus x cubed. That is my transient portion, and the solution is valid all over the place, so I can go everywhere, and c exponential of minus x cubed is the transient. So we're just practicing what does the transient mean. So when you go to engineering, you have a signal or circuit or something, it starts in a certain way, and then you have a component that stays on, it's called steady state, and a component that dies away is called transient, and well, that's it. Okay, all of these problems, we had an interval that was all over the place, and that wasn't all that exciting. So we are going to go ahead and up the ante and take a look at the problems with a bit more turns of twist to it. So example 4 that I listed there was x squared y prime plus xy is equal to 3. Okay, we said standardize, otherwise that approach we have up there is going to get into trouble. So I divide by x squared. So I'll have y prime. So when I divide by squared, I get 1 here. X divided by x squared. What's that? Of course, 1 over x, y. And right hand side, I divide. Don't forget, everybody divides. 3 over x squared. Now we said the integrating factor is the exponential of integral of this coefficient dx. Well, luckily this is not troublesome. It's logarithm of x. Now we need to know something from pre-calculus. What's the exponential of logarithm? Well, that's just the two inverse function, they cancel each other out, we get x. Now what? Now I take this, multiply by the standardized equation, not the original, standardized equation, multiply by x. So what do I get? X y prime plus x times 1 over x is just 1. And right hand side, what do I get? 3 over x squared times x is 3 over x. We went through a rather torturous step to get something that we could have gone easily, perhaps take this thing by divide by x, but let's wait for a moment. Let's see. What is that? That's the derivative of what? That's the derivative of x of y. Because x times the derivative of the other fellow plus derivative of x, which is 1, times the second element and 3. That's y. So I wrote the product rule a little bit different order than before, but doesn't change anything. That's 3 over x. Now, differentiate this thing. So it will become integral of 3 over x dx. And that is 3 logarithm of x. To be correct, 3 logarithm of absolute value of x plus a constant. Isolate y. So I divide by x. And divide by x. Now, one more fact from calculus 1. Logarithm of x. Well, this is our solution. Standard set of questions here is to practice what's transient and so on. You obviously know that that c divided by x, this goes to 0. So what are the transients in this solution? Definitely we see c over x is something that when x goes to infinity, that goes to 0. Interestingly enough, this is also transient. If you know from calculus, logarithm is a very lazy function. It doesn't grow that fast. It loses the competition to x. Logarithm of x to x goes to 0 as x goes to infinity. One of those things that you do by L'Hopital or by somebody. That what that means, it means this component also is a transient component. Now, interesting issue comes up, which is, well, what's the domain of the solution? You see quite a few red flags. When you look at the standardized equation, you notice that you have a function 1 over x or 3 over x squared. Both of these become discontinuous, or we say explode to infinity at x equal to 0. That's a signal for you that x equal to 0 is a problem spot. Everything's going to blow up at that point. So you see that problem here, and then you see it here at x equal to 0 again. You're dividing by 0, the same problem here. And logarithm of 0, let's remember that one. We need it sometimes. Logarithm of 0 itself is a trouble spot. Logarithm of 0 is minus infinity, so remember that from pre-calculus or calculus. So the domain of this, you better stick either to positive side or the negative side. And between the two of them, you see that sometimes the textbook or your software prefers the positive, like positive time values. If it asks for the largest time on which the solution is valid, you pick 0 to infinity. Of course, we could have chosen minus infinity to 0 as well, but tradition is someplace to just start at 0 and move forward. So we have the domain answered here, and that as well. Let's move on to, how much time do we have? We have another equation, problem 5. I have y prime is equal to 2y plus x squared plus 9. And okay, standardization. Oh, I don't need to divide by anything, but bring this guy at least to that side. So y prime minus 2y is equal to x squared plus 9. So that was painless. What is m? Well, exponential of the integral of this coefficient. Don't forget the sign. So minus 2 dx. So that's exponential of minus 2x. So I'm multiplying both sides by exponential of minus 2x. Minus 2 exponential of minus 2x is equal to x squared exponential of minus 2x plus 9 exponential of minus 2x. Left hand side is the easy part. So y exponential of minus 2x. If you take this thing and differentiate, you get that y prime times the second component. Derivative of this, I forgot, this is minus 2x times y. So now I have this stuff on the right hand side. Antiderivative of this simply means the differentiation goes away. Y exponential of minus 2x. Right hand side, I have exponential of antiderivative of x squared exponential of minus 2x plus 9 exponential of minus 2x, whole thing dx. We might as well split this into two parts, easy part and a bit lengthy part. So I have x squared exponential of minus 2x dx plus 9 exponential of minus 2x dx. Here is our challenge. What's the antiderivative of x squared exponential of minus 2x dx? So that is a bit of a pause over there. The other one is easy. 9 exponential of minus 2x over minus 2, and then a constant. Well, so we are almost all done except for this integral. Now, in this problem, it turns out that we can apply some tricks to actually figure out what this integral is. But if the problem was a little bit different, we could easily get stuck at this stage, meaning the integral is just something that nobody has ever bothered with introducing it, creating a function for it, and so on. So every now and then you see these problems that the solution has an integral in it, meaning there is nowhere else to go other than just stop here. And that's okay. So sometimes the problems don't always turn out to be functions that we have seen previously in calculus and so on. Perhaps there are new functions out there, and that is actually the most common situation. The number of functions that are out there is a very large order of infinity, okay? And then all the way through your calculus and pre-calculus and so on. Perhaps you have seen a dozen functions and so on, and that pales in comparison to the list of functions that are out there. It's like comparing a drop to all the waters in all the ocean. So we might have some formulas for this dozen cases or so of functions that we know, but we shouldn't expect that every one of them would yield to our tricks. At any rate, so in this case, we can actually proceed a bit ahead and figure out what this integral is. That's going to be like a few minutes of a separate lecture from calculus classes that you had before. But before we get stuck with that, let's see what do. We multiply both sides with exponential of 2x times whatever this thing is. So whatever this integral is, whenever we get done with that, we take that, and the other one is 9 exponential of minus 2x over minus 2, whatever that one is, and a constant. So that would be a solution, except that in all homeworks, if this is possible to be simplified, you have to simplify it. So let's go and spend a little bit of time on that one. So for that, I need to introduce you to so-called integration by parts. I noticed that I have a sign error here, which happened here. Sorry for that. We had minus, and that minus I forgot to write it here, so this is a minus here, and so this is a minus here, so this is going to be a minus, and then minus x over 2, and then minus a quarter minus 9/2, so 1 and 18 minus 19/4, so I have minus 19/4, and then constant times exponential of 2x. Okay, so the problem took us a bit of a time to do this, and well, how do you do it quickly? There's essentially no way of doing quickly unless you have done this thing on the side. So what I recommend is that you go ahead and write study integration by parts, find formulas for this type of integrals so that you can perform this task quickly. So what does this the problem boils down to the following. If you see x to power of n exponential of, say, ax dx, what is that equal to? You are going to find that in our calculus books, various lectures all over the place, and you make a table of these type of integrals for yourself so that you can perform this problem quickly. So again, the purpose of the course is not to concentrate on integration. That is not the focus of us. So we don't want to spend too much time on this type of problem. That was for calculus. We already did it over there. We don't want to reinvent that wheel. So as a matter of exercise for calculus, that's fine. But let's focus on the stuff that are related to differential equation. And the significant point here was how do you calculate the integrating factor? How does this process work? So let's go ahead after another one of these problems, perhaps. Again, what is the transient component here? There are no transients here. Nothing is dying away. And the solution is valid for all the x's. There are no problems there. And we didn't encounter any of that kind of problems here. Let's go ahead and do another problem. So let's see, problem number 6 I had listed up there was x y prime minus y is equal to x squared sine of x. So let's throw in some trig components here. So what did we say we do first? Standardize. So y prime minus 1 over x y is equal to, so dividing by x. Calculate m, exponential of the integral of, don't forget the sign, minus 1 over x dx. That is exponential of logarithm of x, and exponential of, you can write this exponential of logarithm of x to the power of minus 1, and that is just x. That's x to the power of minus 1, which is 1 over x. So what does that mean? We are multiplying the equation by 1 over x, so it becomes 1 over x y prime. 1 over x times another 1 over x is 1 over x squared. 1 over x times that is going to be sine of x. Oh, I forgot my y again. Looks like I keep making that mistake. Now, what's the left-hand side? The claim to fame of all of the discussion today is that this is a complete derivative of what? That factor times y. So again, double check. Derivative of y times this. Derivative of 1 over x, that's minus 1 over x squared, is equal to sine of x. And then, of course, 1 over x y. Antiderivative of the sine. What's the antiderivative of the sine? Is of course cosine, minus cosine of x plus a constant multiplied through, that is the solution. What is the interval? Again, you come here to standardized equation. You notice that you are dividing by x. It would not be okay to divide by 0 here. And so the interval splits at x itself, at x equal to 0. So our interval, even though this is valid for the entire set of x values, we see that we are separating at that 0. Let's go ahead, take a look at the, remember we had this software. Let's go ahead and investigate the picture for this thing. I have a differential equation that is y prime. Right hand side I carry my I have to write it in the standard. So one other reason to emphasize a standardized form, because here once you want to enter this, you have to enter it in the standardized form here on the right hand side. So I have y over x in my equation, and then plus, what was it, x squared times sine of x. And it's in red, meaning that the software is complaining something is not quite working, because our independent variable is x. So let's make sure that we are all good to go here. We had y over x and x squared sine x, if I'm not mistaken. Let's make some window, and now let's graph this. What happened to my graph? Okay. Okay, you notice that these are different solutions. All of them pass through 0. Now, let's go start a window input, keyboard input. So for example, I might have x equal to, of course I cannot choose x equal to 0. The software is going to complain. Let's see, does it complain? X0, say y equal to 1. What does it do? Did I have any error messages? You see, the software complains. You see all of these things. Software complains, not surprising, because you are forcing it to start at 0, and at 0 this whatever you wrote here doesn't make good sense. So let's go ahead, choose x equal to 1. So that's one reason to have issue of the domain. So maybe I erase this thing and start all over again, if it listens to me. Okay. So something happens at 0. We cannot communicate from right side to the left side easily, and we might as well separate our solution space into two pieces. One piece from 0 to infinity, another piece from minus infinity to 0. And if your software asks for the solution, it just means the positive component for some reason. Okay. So that is the problem for what is it, number 6. And number 7, maybe I leave that to you. It's more or less same thing. So I'm going to go to 8. Uh, y dx minus 2x plus y to power of 4 dy equal to 0. Why did I include this thing? Uh, Sometimes, well, you have two variables here. One is x and one is y. You have a choice as to which one of them to be taken as your independent variable and which one as dependent variable. Sometimes going it one way is a lot easier than going it some other way. Let's see. So here, the way I wrote it, it gives you a bit of a clue that dx is written first, but notice that as far as the equation is concerned, this would be same as writing it as, for example, uh, 2 times x plus y for dy is equal to, say, y dx. Or here's another format of writing dy dx, that's y prime, is equal to y divided by 2 times x plus y to power of 4. These are all equivalent forms of this equation. So here's another one. I can write this thing as dx dy times y minus 2 times x plus y to power of 4 equal to 0. That's another format of it. If you want, you still want more, so y dx dy minus 2x is equal to 2y to power of 4. So one equation, a half a dozen different ways of writing it. Any of them could be our starting point. The question is there an advantage in reorganizing our equation in terms of one variable or another one? So, for example, I might give you this equation to you in this format, but we're going to go and see that this other format is going to be easier for us to approach. Let's see how. Okay, so this equation is given. I rewrote it like this. Now, one more way of writing it, y x prime minus 2x is equal to 2y to power of 4. So what does prime mean here? Prime means derivative with respect to y. We just changed the traditional role of x and y, and we are using derivative with respect to y as our basis. Okay, but the procedure is exactly same as before. I standardize it, so it's going to look like x prime minus 2 over y x is equal to 2y cubed. Then calculate my integrating factor, exponential of integral of minus 2 over y dy. That is exponential of minus 2 logarithm of y. Similar to what we did before, this is exponential of logarithm of y to power of minus 2. Exponential of logarithm is just your function. Y to power of minus 2 is just 1 over y squared. So what do I have to do here? I take my standardized equation, multiplied by, so let's say I have my standardized equation x prime minus 2 over y x is equal to 2y cubed. I figured out that my integrating factor is 1 over y squared. I multiply them, these two equations, I multiply them, so it becomes 1 over y squared x prime minus 2 over y cubed x, and this is just 2y, is that right? Multiplied by 1 over y squared, all the terms, and that's what we get. What have we achieved with all of this thing? What we have achieved is that this is 1 over y squared times x prime, because derivative of x times the other one is the first component. Derivative of 1 over y squared is minus 2 over y cubed times the second one. That is equal to 2y. I integrate both sides, so it becomes x over y squared. Right hand side is 2y dy. Notice that we are doing differential of y in all of these things. Antiderivative of 2y is going to be y squared plus a constant. So I now multiply both sides with the denominator. I get x is equal to y squared times that is y to the power of 4 plus cy squared. Here's our solution. The other way of doing this thing, we had to calculate y in terms of x, and you can notice that it's going to involve lots of radicals, difficult integrations, and so on. So we saved ourselves a bit of time by avoiding all of that. So sometimes you can rearrange an equation, and that could be to your advantage. Again, remember that for our domain, when we divide by y here, it's quite obvious that y equal to 0 is going to be problematic point for our equation and solution and everything. And our domain, therefore, we have to either go on the positive side or the negative side, and here we just choose the positive side. Okay, so we looked at quite a few problems. We had 8 problems. Somehow we actually managed to do 8 problems. So integrating factor method is important. Now, why do we learn all this algebra here? Because this type of equation show up all over the place when we apply modeling to engineering or physics problems. So the motivation came from there, and all these algebra methods or calculus methods are aimed at solving those problems and understanding the issues that come up. Okay, until next time, good luck and God bless.